Hey everybody, just want to take a time and just share something with you tonight. I love Supernova, so much so that I've done a Supernova challenge, which I've posted about. I've shared multiple times. It's over at Adventures in Deep Space. It's on my blog. It's here on Patreon under EadsyAstronomy. Love chasing them down. I love viewing the remnants. Would love to actually see supernova in my lifetime. One here in the Milky Way. I've seen them in other galaxies in my life. Really would love to see one in the night sky here before I leave my time here on Earth. We'll see if that ever happens or not. But I want to talk about one that happened, we estimate probably about 1680, give or take. We're not quite sure. It happened in the constellation of Cassiopeia. It's called Cassiopeia A, or Cas A. It began with a massive star, likely a red supergiant. It had to be bigger than 8 times the mass of the sun. And around 1680, the star's inner core collapsed, resulting in a violent supernova explosion. However, this event basically went largely unknown about and unseen, because we know that there was interstellar gas and large dense clouds of gas that were stopping visible light from reaching Earth. Between the dust and the interstellar gas, it just absorbed all the light coming from the supernova itself. It's possible that an English astronomer royal, John Flamsteed, may have recorded the supernova as a faint 6 magnitude star in 1680, but this remains really a subject of debate. There's a lot of controversy with that, whether or not that actually happened among historians of astronomy. For nearly 3 centuries, the remnant remained undiscovered, unknown of, and it just continued to expand silently into the interstellar medium, which supernova remnants do. Then in 1947, it was finally revealed. Cas A was found, and it was revealed not by light, but by radio waves. The radio astronomers Martin Ryle and Francis Graham Smith at the University of Cambridge were surveying the sky using early radio telescopes. They detected an incredibly powerful, just a real powerful source of radio emissions coming from the constellation of Cassiopeia. And Cassiopeia, just to remind those who may not know, is that W up in the northern sky. If it's inverted, it can look like an M. I always see it as a W. So it's usually great in the fall, early winter. Right now is a great time to view it. Late summer, actually, through early winter is a great time to view Cassiopeia and the objects up there. Following the naming convention, once these two famous astronomers found this object using radio telescopes, relatively new ones, for bright radio sources, they named it Cassiopeia A. It's the brightest extrasolar radio source in the sky at frequencies above 1 gigahertz. The discovery was a cornerstone in the burgeoning field of radio astronomy, demonstrating that the universe was filled with objects invisible really to traditional optical telescopes and those type of means. Then on August 28th of this year, NASA released a study about the final hours of this star that exploded, creating Cassiopeia A. The article release is called, it's a website, I'll put it on the page here, called NASA's Chandra Reveals Stars Inner Conflict Before Explosion, and it revealed new information about what happened in the star's last hours before it exploded as a supernova. The study, using data from NASA's Chandra X-ray Telescope Observatory, looked at the elements inside the star right before the explosion. And I'm going to minimize my image here, which is showing it. And as you can see, most massive stars have layers, and here you can see the layers as they're shown here. You have the hydrogen, outer core, hydrogen helium fusion. As hydrogen begins to fuse, it will fuse and create helium. Helium fusion then will take over, You can see that layer coming in here as helium heats up and begins to put a core down of ash. That ash eventually is lit up, and we get into carbon and oxygen fusion here. As ash builds up from that nuclear fusion reactions, it builds up a magnesium, then a neon, and then oxygen fusion that's happening here in this layer of the shell. And then as that creates ash from the burning, silicon sulfur fusion happens. Finally, what that does is begin to lay down an iron ash, and when that iron ash gets to the Chandrasekhar limit of 1.44 masses, the core can no longer sustain itself. It collapses, and that collapse causes a shock wave to come out, blowing all these other layers out, actually creating other heavier elements greater than iron, and blowing it out into the interstellar medium, where eventually it's used in new creation of stars and planets and things like that. Anyway, that study, again, looked at the elements inside the star right before it exploded, and what the scientists discovered was that in the final hours before the star blew, its interior just really began a violent shuffle. And I'm going to scroll down because I've actually taken an image from the Chandra site on this to kind of show this. Normally, like I said, a massive star has layers, kind of like an onion, and I showed that there. Okay, and in Cas A's case, a layer rich in silicon, and you can see that here. Here's that layer rich in silicon, violently pushed its way outward into the neighboring layer rich in neon, and neon begin to push down on the silicon layer. So they begin to push outward, push inward, and as a result, this intense inner churning may have been the final trigger that caused the star's explosion to succeed and happen. It also explains why the cloud of debris left behind, the Cas A remnant as we call it, is not perfectly round. I'll show you that in a few minutes. And why the collapsed scar of the star, now a neutron star, was given a powerful kick, making it shoot away from the center of the explosion. This was considered really the youngest supernova for once it was discovered, being only about 300 years old, until 1984, when the VLA telescope discovered and confirmed a discovery called G1.9 plus 0.3. And then in 2007, Chandra was put on it, the Chandra X-ray Observatory. And there you can see what Cas A kind of looks like today. It's not perfectly round. There's a lot to it. But in this study, that's just showing you the silicon and neon rich part that Chandra found in this little section here. But going on, G 1.9 plus 0.3 was found by the Chandra X-ray. There you can see it. In 2007, it was confirmed. VLA went back to it in 2008. And when Chandra looked at it, Chandra said this was 15 times larger, 15% larger than what the VLA estimated in 1984. In 2008, VLA was put back on it. That telescope observed it again, and it verified that it was indeed 15% larger, but put an estimate on it at about 150 years. Further studies since then have narrowed that age down to about 110 years old, and it also revealed that this supernova was formed by the collision of two white dwarf stars, making it a type 1A supernova. So in both these cases, with Cassiopeia A and with G1.9 plus 0.3, we did not see either of these because of the dust and interstellar gas that absorbed the light, blocking it from our viewpoint on Earth, so the visible light never reached us. It's probably why we haven't seen an observable supernova in over 400 years, because like in these two cases, the interstellar dust and interstellar gas have created a barrier to where it absorbs the visual light as it's coming. So we haven't been able to see. We know these two have gone off. We can see the remnants. And anyway, we can definitely tell that these have gone off, and probably others have gone off that we're just now starting to look at and perhaps discover. So to me, Cas A is a fascinating object in the night sky. It's a supernova remnant. It's amazing to me. If you think about a supernova remnant, the elements that it puts out helps to form planets, other stars, and even life itself. The iron in our blood, running through our veins, it's the result. It's coming from an exploded supernova star, a massive star that exploded into supernova and sent those elements out and into the interstellar medium, and they eventually condensed, and our sun was formed from it. Other stars were formed from it, but around our star, planets formed, and as I talked about in another one, our star kind of got out of the way of its open cluster within 50 million years, leaving our planets on an equal plane in our solar system and allowing for life to develop on Earth. Those elements were used when the star and our sun and the planets around it formed. So taking those elements from an older exploded supernova remnant and recycling those elements. So kind of cool. Yes, I have observed Cassiopeia A 4 times. I'm going to kind of go through and share those and discuss how you can go about finding them. And I'll actually pull up right down here, Stellarium. We'll launch that. And as that's launching, let's talk about it. Cassiopeia A is a fantastic object to go. It's very faint. You need to be skilled in seeing it. It's an observing challenge if you haven't done it. And it's really ironic to me that Cas A is visible. It's largely visible, even though it exploded in the late 1600s. Even though parts are visible, mainly it remains invisible to the human eye. It took Chandra with X-ray and radio telescopes to discover it, as I've talked about. It's not going to look like the Orion Nebula when you look at it. It's not going to look like the Ring Nebula. It's not going to look like the Swan Nebula or any of those nebulas. It's not even going to look like the Veil Nebula that you can look at in the summer in Cygnus. It really is a challenge object intended for experienced observers with good equipment. I would say you need at minimum a 10-inch scope. 12.5 or greater, I would recommend. 15 and greater, really to nail this down. You also need some good eyepieces. You need a filter, 03 narrowband. Helps to see this. Make sure, here we go, we got Stellarium coming up. And so I'm just going to come down here and bring up the constellations, and we're going to mark deep sky objects so that they come up. Hopefully, come on. There we go. Okay. And we will go and find Cassiopeia right there. And we will pause. I'm going to pause this so that it doesn't interfere. Sorry, I got a bunch of stuff in front of my monitor right now, and I need to just pause this. I just want it there. You know, I'm looking at, it's 11:41 Mountain Time here, so Cassiopeia is high in the northwest sky right now, and this would actually be a really good time to go after this object this late at night. You need really good transparent skies to see this. Aperture, you truly need a telescope that's at least, some people recommend an 8-inch. I really recommend a minimum of 10-inch to really a 12.5-inch probably to begin to see some of the structure. 15-inch or larger, that's when it gets interesting to view this. I have viewed it with my 14, I've viewed it with my 17.5. I mainly use my 17.5-inch telescope Dobsonian to see this. You also need dark skies. I'm not going to go in my backyard and star hop to this object and then find it in my MPAS 19.1 to 19.4 skies in the backyard, especially with the neighbor with his big light, motion light on. You need to be in a dark sky. Light pollution is the enemy of this object, and it will kill it. I would say Bortle 4 borderline Bortle 3. I would say 21.5 if you're using an SQM or above to really get a good view of this. And you definitely want the moon out of the sky. It's best to see it during new moon time. You really do need an O3 filter. I've always used one of my O3 filters on this, both in the 2-inch and 1 1/4, depending on the eyepiece I'm using. The visible light from Cas A comes almost entirely from ionized oxygen, so that's why you need the O3. Without a filter, the remnant will blend right into the background stars of the Milky Way. O3 filter darkens that background and the stars, while allowing the specific wavelight of the nebula or the supernova remnant to be able to come out and to be seen. A UHC filter, which I mentioned in narrowband, is a distant second best. O3 is the preferred one on this object, I feel. Don't expect to see what I've shown earlier, what Cas A looked like. It's not going to be that vibrant color. I'll actually show you here in a minute what it's going to look like. Let's talk about how to get there. You're going to go to Cassiopeia. Here you can see it's starting to look like an M for some people. I still see it as the W. But you're going to go to CAF. And from CAF, you're going to probably want to come down to the Carolyn Rose cluster here, and we'll just click on that and bring it up. That, as you can see, is NGC 7789, and from 7789 you're going to come in here and you're going to find, and Bob King in Sky and Telescope has some star charts that I'll also include in the post so you can use those. You're going to come here, and just so you know, we'll bring it up really quick. You can see I've had it up as I was practicing. There is where Cas A is. So from the Carolyn Rose cluster, you want to look really carefully for this little parallelogram thing, asterism that occurs here. And you're going to want to go there. And then what you're going to want to do is star hop down. And this is what I do. I start from NGC 7729 Caroline's Rose Cluster. And I come down, and you can either come to right here to 5 Cas. And then hop down. See, I usually go to here. Then I get 3 stars here. I hop over these 3 curved stars. And then my ultimate goal is to come down here to AR Cas. We'll zoom in. AR Cas is a double star, so if you're using magnification, you can see that. And then it's just a matter of coming across, and let me bring it back up. Once you get to AR Cas, then what you're going to want to do is come down, and I look for these 2 stars. And then I come down and I look for that star, and then with the O3 filter in, I can begin scanning. And this is the portion of the supernova remnant that you're actually going to observe. Okay? So again, it's not the only way you can do it. Some people come in and they can go from Perseus, or from Cepheus, going from right here, going from 32 Cephi Cepheus, and then we'll bring up Cas A again. You can see it's right there, and they work their way over through these stars, up through that little triangle, and then just come over, and they get back to AR Cas. And once you get to AR Cas, you just want to come down just a little bit from AR Cas, and then start using that O3 filter in a wide field eyepiece, and come in and keep going until you go past those stars and these stars, and just start scanning for Cas A. And I'll leave probably a better direction there. So again, you want to locate those. I would start with starting at CAF right here in there, and then going down and You can also come down, and I would go to Caroline's Rose Cluster 7729, and then work my way over and down to AR Cas, and then just come down a little bit from AR Cas using a wide field lens and eyepiece and an O3 filter attached. Another way to do it is you can, and let's bring that up, M52. You can see M52s right here. A lot of people do it this way. They go to CAF and they work their way down to M52, the salt and pepper open cluster. And then from M52, they work their way over here to HP 115395. And it's basically, you can think of it this way, from M52, it's about 3 degrees, roughly 2 fingers width out of arm's length southwest of M52. You can see, if I bring it back up, sorry about that, just really trying to help you get a direction here of where it is. And you can use Stellarium yourself or Sky Safari, PyFinder, anything like that. Digital setting circles will help you get there. But it's about 2 fingers width, almost directly across. You can see there's the salt and pepper cluster. Some people then go to the Bubble Nebula, come over to these 3 stars, getting to here, and then just working their way over to Cas A right there. And so there's several ways you can do it. I've done it both ways. I would just suggest that you try it and decide which way works for you if you're star hopping. If you can center that, excuse me, look for a magnitude 5. The final hop from Cas A is, like I said, 3 degrees. Look for a magnify. If you're coming from M52 in the bubble, look for the magnitude 5 star easily seen right here in the finder scope, located between M52 and Cas. Actually, they're talking this one. Cas A is located just a tiny bit, about 15 arc minutes northwest of there, which is again here. So that's how you find it. Let's go ahead and get out of here and come back. Once you get onto Cas A, and you can see a hint, you do need to remain dark adapted. You want to make sure all lights are off, excuse me, and that your eyes are fully dark adapted. I would say 30 minutes with no lights around. That's what you're going to need. You can try the blinking technique where you move the filter in and then out, and by doing that you can detect the slight nebulosity of the supernova remnant, which I'll show you in a minute in my sketches. You can use averted vision, which is to look directly at the object, look a little bit off, and then see by looking a little bit off what you see in your peripheral there. That's helped me. Usually once I grasp it, I can hold it with my direct vision. Some people say tap the scope. I don't have to tap. I can use averted vision and my O3 filter, and coming down from a wide field, low power eyepiece to a more mid-range eyepiece with the filter on helps me to see this, and then I usually bring a higher power eyepiece to view it. What does it look like? Well, I've posted it up here in GIMP, and I'm going to just go through, actually have several sketches of it here. This is probably the most recent one here, right here, and we'll go through each of these. And then I have another one. It's probably this first one I did. We'll talk about that in a second. And also got another one right there. So we'll talk about it, and you'll see there's a little bit of variance each time I saw this. First one I saw was way back in, the first time I saw it was, I believe I have it written down, September 27th, 2016, 10:40 p.m. This was out on Forest Road 006 at an Antonati 1 sky. Excellent transparency, very good seeing. It was clear and cool that night, about 40 to 45 degrees. It was in my 17.5-inch Dob. Did have the Paracord 2. I used the 22mm Nagler T4 to star hop, And then I was using my Thousand Oaks 2-inch filter, and then I took it down to a 7mm Pentex with a 10mm. In this case, I did go the M52 route, then I went to the bubble, and then to a small triangle from the left corner, went up 3 stars in a row, started looking for the O3, and the O3 popped it right out. It's faint, it has wisp to it, it's thicker than I really thought it would be, and basically you can see here, it just looked like a really faint and thin streak here in this observation. The next observation that I did, the next sketch, was again in 2016. In this case, let's go to that one. I believe it is going to be, let's see if it's this one. Yes, this is the next one I saw it. Again, that first one was September 2016. Took a look at it again just to confirm that it actually got there on December 30th, 2016 at 8:10 Mountain Daylight Time. Again, out on Forest Road 006 south of Vernon, Utah. I called this Juniper Grove. Would now be called Site 2. It was cold that night, 15 degrees Fahrenheit. Antonati 1, excellent skies again for transparency. Excellent seeing that night. 22mm Nagler T4, 10mm and 5mm Pentex XW with a Paracore Type 2 and an O3 filter. I was able to star hop to the location of Cas A. Tonight I went from Cas to Carolyn Rose and then down to AR Cas and then slightly below, and found the supernova remnant. The arc struck out a lot brighter than it did the first time I saw this, with an equilateral triangles easily seen. I could see this with direct vision. I could see with averted vision, and averted vision brought out a little bit more details, and also could make out right here some of the brighter nebulosity. So using a higher eyepiece, I saw the curve the last time. This time, through the stars, I was able to see more of that faint nebulosity. And that's about how it looks. It's not going to be colorful. It's not going to be like an image. This is what it's going to look like in the eyepiece. The next time I saw it was on this one. No, let's see, is it this one? Nope. Nope. Let's see. No, that's the same one. Looks like I didn't bring it up. Let's bring it up. File, open. Should take me right to my Cas A. This would have been 11/7/24. Looks like I need to upload it. I'll have to do that. So it's in here. I just need to find it. Let's see what this one looks like. Sorry, I really should have had this more prepared. No, sorry, that's not it. That's a sketch of the Lagoon Nebula that I'll be sharing. So file, open, which you can see down here. I've already processed that one in GIMP a little bit. It's pretty bright. Let's see, just gotta remember which one I actually did this to. I'm gonna pause really quick. Okay, I found my next sketch. This was done on November 7th, 2024. It was an Antonati 1 night. Excellent transparency, very good scene. Did it in 17.5, actually Antonati 2 on there. But still excellent on the back. It's telling me excellent transparency, very good scene. O3 filter, 10mm Pentax XW. 22mm T4 Nagler was the finder. Again, 17.5-inch job, which you can see up here in the corner. Notes on the back tell me that with the O3 filter this night, I was able to discern a lot more of, I could still see the main arch here with some brighter knots and modeling to it. Also saw a segment over here leading off to here, and then just a hint of a southern segment, a branch as you're heading down toward the southern, the segment down here. There. So this was probably the best view I had. Again, it's a very faint object. You're not going to make out tons on this. And then the next one, if I have it right, should be this one, which it is. This one was done on August 20th of this year, 2025. It was done at Forest Road 006, Site 2, Antonati 1. Excellent transparency, good scene. This was seen in the 28 millimeter UWA, also with the 20 millimeter XWA 100 as the finders, with O3 filters present. I then used the 13 millimeter, the 9 millimeter, and the 7 millimeter XWA to observe. 17.5 inch Dob, f4.4, Paracord 2, O3 filters. The north end was the brightest, with the southeast end very faint. Averted vision gave me the blob across from the crescent shape of the supernova remnant, which is located right here in the observation. Fun observation. Tried to make the sketch very realistic here from what I was seeing. I used star hops. I star hopped to Cassiopeia, and then to Carolyn's star cluster, and then to ARS, and then to Cas A, and put in the O3 filter. I followed Bob's King's path beginning at NGC 7789, then star hopping 3.5 degrees southeast of King 20 to an open cluster. King 20 is just east of a mag 4.9 variable star AR Cas, and then from there I went southwest of AR Cas about 1 degree, nailed Cas A. Cas A is very elongated, fuzzy, resembles a small galaxy to me. Switching to the 13 millimeter and then the 9 millimeter and the 7 millimeter XWA with the 2-inch filter. Fuzzy pops into view more easily with the filter, and make no mistake, it is faint. It is very faint. But even though it's faint, as I say in the notes right here, it is observable. You will be able to make out Cas A, and you can see some brighter portions of it, and then with averted you can kind of see that, and then averted brought out the little blob right here. Again, this is not for the faint of heart. You want to be experienced. If you're new, it could be a really good challenge object regardless of your ability, but if you're new, it's going to be extremely challenging because you've got to get your eyes used to seeing faint objects, but it is observable. One of the things I wanted to share in this observation is I think it's awesome. Two things. I think it's awesome that we can actually see a supernova remnant from a star that exploded and understand the science behind it. I like to connect the science with what I see and observe visually. I need to put the C star on it and see what I come up with the C star, if it will grab anything from it. But it is visually observable. I'm not the only one that's done it. There's plenty of others. I've done it multiple times, and you never know what you're going to see unless you try. Again, though, I do think you need at minimum, some people say an 8 to 10. I would say a 10 to 12 and a half. I would prefer the 12 and a half minimum. If you really want to start to see some of the brighter structure and stuff with the filter, I would say you need to be 15 inch and above in your telescope size. Fun object, ties it all together, wraps it up. This is why I love observing. This is why I love astronomy. I can make connections, personal connections here, and it allows me to really enjoy what I'm doing when I do that. And I love the ability to sketch. I hope you have clear skies, both in your personal life and in your night skies above, that you're able to get out and find some of these more challenging objects. The bright ones are always fun to look at. I also enjoy having to go and find these objects for myself. So there you go. Have a great night. Hope this is helpful. Talk to you later.